AP waves number 4. Let's look at our first problem. A ball is thrown, has initial velocity of 8.468 and travels a horizontal distance of 7.3 meters, and they give us a time of 1.25 seconds. Remember, anything flown in the air is going to follow the shape of a parabola. First, we need to find the weight of the ball. Weight is the same thing as the force of gravity. It's m times g. Part B, the initial kinetic energy of the ball. Kinetic energy is 1/2 mv squared. They gave us the speed of the ball and the mass of the ball, so we're just plugging into the formula. Part C, the angle of the ball's initial velocity with the horizontal. Our initial velocity is v0, and we're going to have to make a triangle down here. I can use the distance and the time to find my vx, and then we can use the cosine formula to find our angle. Right, so in the x direction, remember the x direction only has one formula because there's no acceleration in the x direction. So it's just the distance divided by the time. Comes out to 5.87 seconds. So I'm going to do the inverse cosine of Vx over V0 and end up with 46 degrees. Question number 2, you're traveling in a train, 55 kilometers per hour, you're approaching a bell, and we give an initial frequency, and they want to know what frequency do you hear. This is a Doppler effect formula. First, I want to change my units here to meters per second, because I know the speed of sound in meters per second. You are the observer, and the source is the bell. The source is not moving, so it had a speed of 0, and you are moving towards the bell, so you have a positive velocity. Comes out to 758 hertz. After you get an answer, you want to go back and think about it. If you're going towards something, will you hear a higher or a lower sound? Towards should always be a higher. An 18.5 centimeter pipe is open at one end. Open at one end means it is a closed pipe. What are the frequencies of the first 3 harmonics? Remember the closed pipe formula, we do odd numbers for the ends. So our first frequency is the first harmonic times the speed of sound over 4 times the length. And then for the second and third harmonics, we can substitute in place of 1, the 3, and the 5, because we're counting by odd numbers, or we can do the shortcut. The third harmonic is 3 times the fundamental, and the fifth harmonic would be 5 times the fundamental. Part B, what is the wavelength of the third harmonic? We're going to use the wave formula, which is speed equals frequency times wavelength. And dividing by frequency, we're going to take the speed of sound in air divided by the frequency to get our wavelength. Problem number 4, draw a picture of a pendulum showing its swing. So I've labeled the highest points and the lowest point of the pendulum. We want to label the point of maximum velocity. We're going fastest down at the bottom. The point of minimum velocity at the very top, it comes to a stop before it goes back down again. The point where the potential energy is the greatest, that would be the highest point, either one of the top points. The point where the kinetic energy is greatest is where it's going to be going the fastest, down at the bottom. If the period of the pendulum is 0.75 seconds, what is the length? We're going to use the period formula and rearrange for L and plug in the numbers. I got 0.140 for the length. Last one, number F. We walked through this in one of our labs, and I realized I didn't pass the lab back yet. What is the speed of the pendulum at the bottom? We're going to do conservation of energy. When you're pulling the pendulum back, you're giving it potential energy, and then it changes to kinetic down at the bottom. So we need to figure out what is this height that we're lifting the ball up. What is this length right here? I know the length of the string I'm going to call L. So this side, using the triangle, this side is going to be L cosine theta. And if I subtract this length and this length, that will give me the height that I need. So the height is L minus L cosine theta. Factoring the L out, we get L times 1 minus cosine theta. So the kinetic energy is coming from the potential energy, so I'll put those two formulas equal to each other. And remember, when we do this, the mass is going to cancel out when we're solving for V. And then I'm going to substitute this H into this one. So we get, this is the formula for the velocity of the pendulum down at the bottom. Plugging our numbers, I come out with 0.225 meters per second. You have a really hot new car. It has one of the most outstanding audio systems available. Anyway, it can go faster than the speed of sound. So when you're out tooling down the test strip at Mach 2, twice the speed of sound, can you hear the stereo? Explain your answer. The answer is yes, you can hear it. Because you're both going the same speed, it would be the same as if you were sitting still. And the example I usually give of this is we're all on the Earth. The Earth is going 68,000 miles per hour. And to us, everything acts just like as if we were sitting still, because we're all moving together at the same speed. Number 6, frequency. We're just using the wave formula. Speed is wavelength times frequency. And you have to recognize that a radio wave travels at the speed of light. Number 7, we have two masses hanging over a pulley. We let go and they're going to accelerate. We need to find the acceleration of the system. Drawing in my forces, I have tension pulling up on both of them and their weight pulling down. For the first object, sum of the forces, we have tension pulling up and gravity pulling down, and that's going to equal to ma. And that tension is the same tension that's over on this string, which is coming from this other mg. So I'm going to substitute that mg in place of the tension. And then we're going to rearrange this for a. I'm factoring the g out of the left side, and then I'm going to divide by the mass on the right side. Plugging in the numbers, I got 0.0457 meters per second squared upwards. Pulling a crate at an angle of 25 degrees. We did this problem on the Box on a Hill page in the CP class. This one works exactly the same way. However, occasionally on an AP test you'll have a problem where they don't give you any numbers. So I'm going to go through this problem and solve it as if we didn't have numbers and then plug in the numbers at the end. And this is what I would like you to do to practice when we're doing these problems, so you can get used to doing one of these problems when they don't give you any numbers. First of all, we have a force being pulled at an angle, so we need to find components on it. And remember, in the AP class, they don't call it Fx and Fy anymore. This is just Ft cosine and Ft sine theta. Sum of forces in the y direction. There's 3 forces in the y direction. And I know in the y direction, they always add up to 0. We take the forces going upwards, subtract the one going downwards, and that equals 0. Rearranging, we're trying to find the normal force, so we can find the friction force, so we can find the acceleration in the x direction. Friction formula is mu times Fn. Then in the x direction, we have Ft cosine theta is pulling forwards and the friction is pulling backwards. And those are going to add up to ma because we're accelerating. So I'm going to substitute mu times Fn in place of Fr. Then I'm going to substitute Fg minus Ft sine theta in place of Fn. And all of that is equal to ma. Here I'm distributing the mu to both of these so I can combine the like terms over here and factor out the Ft. This extra 2 algebra steps is not necessary, it just makes it look more simple to me. Dividing both sides by m, this is a formula for the acceleration then. Then we can plug in our numbers, and I came up with 0.0428 meters per second squared. Now again, on the AP test, you can do each one of these as a separate step and come up with a number and plug in the number for each one of these substitutions. I'm showing you the process because there may be a chance they'll give us a problem like this with no numbers on it, and this is the answer they want, is that formula right there. Part B, how much time does it take to drag across the floor? We just got an acceleration. We're looking for time. We know the distance they're dragging it. We need one more variable to do a kinematics formula, and that says the crate starts at rest, so our initial velocity is 0. So we need a kinematic formula with a, t, d, and v in it, is this one. And since our initial velocity is 0, that cancels out. We'll rearrange the rest for t, plug in our numbers. I got 10.8 seconds.